Welcome to the second outcome, where algebra turns visual. Here we learn to picture a function as a curve and to read its story straight from the shape. Geometry in this outcome means sketching and recognizing the graphs of functions on the xy plane. We'll sketch quadratics, cubics, the exponential and logarithm curves, and circles, and see how each one shifts or stretches when we tweak the function. A sketch isn't a painstaking table of plotted points. It's a quick drawing that captures the shape, where the curve crosses the axis, its turning points, and any asymptotes. Let's sketch y equals x squared minus 2x minus 3 by finding its key features first. Since a is positive, the parabola opens upwards in a U shape. Factorizing 2x minus 3 times x plus 1 gives x-intercepts at x equals 3 and x equals minus 1, and putting x equal to 0 gives a y-intercept of minus 3. Completing the square to x minus 1, all squared, minus 4, puts the lowest point, the vertex, at 1 minus 4. The discriminant is a shortcut for knowing how a parabola sits before you draw it. If b squared minus 4ac is greater than 0, the curve crosses the x-axis twice. If it equals 0, it just touches the axis at its vertex. And if it's less than 0, it never reaches the axis. Combine that with the sign of a, which tells you whether the curve opens up or down, and the whole shape is fixed. Let's see where y equals x squared minus 6x plus 9 meets the x-axis. The discriminant is minus 6, all squared, minus 4 times 1 times 9, which is 36 minus 36, exactly 0. A 0 discriminant means the curve touches the axis at a single repeated root, and factorizing to x minus 3, all squared, puts that point at x equals 3. So the vertex sits right on the axis at 3, 0, and the whole curve rests on or above the x-axis. A cubic, whose highest power is 3, has a gentle S-shape and can cross the x-axis up to 3 times. Take y equals x plus 2 times x minus 1 times x minus 3. Reading straight from the brackets, its roots are at minus 2, 1 and 3. Because the leading term is positive, the curve rises away to the right and falls away to the left. Reading a graph from its factorized form like this is far quicker than plotting points one by one. The exponential curve I equals e to the x passes through 0, 1, stays positive everywhere, and shoots upwards steeply, which is why we use it to model rapid growth. The x-axis is its asymptote, a line the curve creeps towards but never touches. Its mirror image, y equals ln x, passes through 1, 0, only exists for x greater than 0, and has the y-axis as its asymptote. Each is the reflection of the other in the line y equals x. Once you know one graph, transformations let you build a whole family from it without plotting anything new. Adding a 2f of x moves the whole graph up by a, while multiplying by a, as in a times f of x, stretches it vertically. Changes inside the bracket act horizontally and, a little counterintuitively, the opposite way to their sign. F of x plus a shifts the graph left by a, and f of ax squashes it horizontally. The rule to hold on to is that inside the bracket changes affect x and outside changes affect y. Let's line those four up against y equals x squared to make them concrete. F of x plus 2 moves the curve up by 2. 3 times f of x makes it 3 times taller. F of x plus 1 shifts it one place to the left. And f of 2, x squeezes it to half its width. It's the same parabola each time, just repositioned or reshaped. Let's put that to work. Suppose y equals f of x has its minimum at the origin, 0, 0, and we want the minimum of y equals f of x minus 3 plus 2. The x minus 3 inside the bracket shifts the graph 3 to the right, and the +2 on the outside lifts it up by 2, so the minimum travels from 0, 0 across to 3, 2, while the shape and width stay exactly the same. A circle with centre AB and radius r has the equation x minus a, all squared, plus y minus b, all squared, equals r squared. So a circle centred at 2 minus 1 with radius 3 has the equation x minus 2, all squared, plus y plus 1, all squared, equals 9. Notice the y plus 1 comes from b being minus 1, and the 9 is 3 squared. Every point on that circle sits exactly 3 units from the centre. When a circle's equation is jumbled up, completing the square untangles it. Take x squared plus y squared minus 4, x plus 6y minus 3 equals 0. We group the x terms and the y terms, then complete the square on each. That turns into x minus 2, all squared minus 4, plus y plus 3, all squared, minus 9 equals 3. Tidying up gives x minus 2, all squared, plus y plus 3, all squared equals 16. So the centre is 2, minus 3, and the radius is the square root of 16, which is 4. There are 2 ways to describe a curve. Cartesian form links x and y directly, like y equals x squared, or x squared plus y squared equals 25. Parametric form instead gives x and y each in terms of a third variable, a parameter such as t. For example, x equals 3 cos t and y equals 2 sin t. To get back to Cartesian form, you eliminate the parameter, often leaning on the identity cos squared t plus sin squared t equals 1. Let's take x equals 3 cos t and y equals 2 sin t, where t is the parameter. As t runs from 0 all the way round to 2 pi, the point x, y traces out an ellipse. To convert, we note that cos t is x over 3 and sin t is y over 2. Then feed those into cos squared t plus sin squared t equals 1. That gives x over 3 all squared plus y over 2 all squared equals 1. Or neatly, x squared over 9 plus y squared over 4 equals 1. Here's a simpler conversion. A curve is given by x equals t plus 1 and y equals t squared. We make to the subject of the easier equation, so from x equals t plus 1 we get t equals x minus 1. Substituting that into y equals t squared gives y equals x minus 1, all squared, which is a parabola with its minimum at 1, 0. Let's pull the geometry together. Sketching always starts by recognizing the family, whether it's a parabola, a cubic, an exponential, a logarithm, or a circle, then marking the key features like intercepts, turning points, asymptotes, and any center or radius. Transformations let you grow new graphs from ones you already know, and parametric form is especially handy for describing paths and motion, which you can always convert back to Cartesian to see the overall shape. So, to recap the second outcome, a good sketch shows a curve's shape and key features rather than a grid of plotted points. For a quadratic, the sign of A gives the direction, and the discriminant gives the number of x-axis crossings. E to the x and ln x are positive and defined mirror images in y equals x. The 4 transformations shift and stretch any graph. And a circle is x minus a, all squared, plus y minus b, all squared, equals r squared, unpacked, by completing the square. That wraps up our tour of graphs and geometry, from sketching quadratics and circles to shifting and stretching whole families of curves. The best way to lock this in is to sketch by hand, always labelling your axis crossings and turning points. For more, the reading list recommends Core Maths for advanced level and the CGP guides. And online, you'll find plenty of graph sketching practice on Maths Genie, Dr. Frost Maths and Khan Academy. The unit's ebooks and journals on Moodle are there too whenever you'd like another angle on a topic.